Swayam Prabha. Digital India. Educated India.
Okay, so now let's look at some of the important results in this probability called convergence in weak convergence and strong convergence. So did we already define what we mean by IID sequence, or we have not yet formally defined it? We have said it, right, what we mean by IID sequence, independent and identically distributed. When we have a sequence of random variables, we actually did this when we are trying to define joint distributions of a sequence of random variables, right. So what we mean by independent, that so if I say that if I have a sequence of, I have a random process, I am going to say this is to be IID if each of my random variable is independent of others and all the random variable in this sequence have the same distribution. Okay, this is as simple as that. Okay, now let's talk about then we have the following results. So let xn greater than n greater than or equals to 1 is such that expectation of xn is finite for all n, and then we are going to define Sn to be summation of xi's I running from 1 to n divided by n. So this is the average of the first sum of, this is the average of first n terms. Okay, then if So let us say right now I have this given sequence of random variables where all of them have the same mean, that is the expectation of xn is going to be m for all n, and this m is assumed to be finite, that is mean of all these random variable is finite, and I have defined this xn which is the average of the first n random variable. Then we are going to say that if further each of my random variance of my random variables is bounded, okay, and their covariance of any pair of random variables is 0, then this Sn by n, what I mean, so Sn, so sorry, I have to be careful here, I am going to define Sn to be simply xi I had to 1 to n. So this is just the sum of the first n random variable, and if I am going to look at their average Sn by n, that converges to this m in the mean squared sense. They are upon bound, they are bounded by the same constant, okay, they are uniformly bounded but need not be same, and we are saying their pairwise covariance is 0. What does this mean? Okay, so this is uncorrelation, we are saying they are uncorrelated, that means they are pairwise independent. It is not that they are independent, this sequence in this bullet A, we are not saying that this sequence xi are independent, okay, we are only saying that they have the same mean and their variances are bounded. Then the second point says that if these sequences are IID, right, in that case what, they are all independent, in that case they have to have the same, necessarily the same mean, and also they necessarily have to the same variance. If that is the case, then they converge in probability to the same value mean, and one can show a stronger result under the same IID assumption that this sequence convergence in almost sure sense also. We know that almost sure is a stronger notion than convergence in probability, right. So if we can show C, that already implies B. Okay, so this part, the B part, often called as weak law of large numbers, and the last part is called strong law of large numbers. Okay, let us try to understand the first part, why that is true. So if I want to show that Sn by n goes to m in the mean squared sense, what I need to show? I need to show that of Sn by n by m, this goes to 0. If this goes to 0, then I can argue that Sn by n converges to m in the mean squared sense. Okay. So what is the mean of Sn by n? Okay, before that, what is the mean of S of n, Sn? It is going to be n times m, right? Because I can just, this is nothing but the sum of the n expectations, where each one is value m. So the expected value of Sn minus n is already m, right? So this is nothing but, then in this case this is nothing but variance of Sn by n, right? So if this is variance of n, I know that this is nothing but 1 by n square of variance of Sn, right? And we already know that this, we can write it as 1 by n square, this is covariance of Sn with itself, correct? When we say that variance is nothing of a random variable, nothing but its covariance with itself. Now if you expand this, so Sn is nothing but the sum of n terms here, this is also sum of n terms, and we know how to find the expected covariance of such terms, right? So if you are going to expand this, what you are going to get is, we did this exercise I think, right, sometime back in the class. That value turns out to be simply covariance of xi minus xj, and we know that when I and j are different, we are going to use this uncorrelatedness property, and because of that, if you simplify this, this is nothing but covariance of xi I1 to n. And now covariance of xi with itself. This is nothing but its variance, right? And what we said, variance of xi is upper bounded by c. We are going to make use of this assumption that we are making. So if you do this, what is this going to be? So c by n, and this c we are assumed to be finite, right? So if I let n go to infinity, this go to 0. So now is this true that this guy Sn by n converges in mean squared sense? So that is what we have exactly proved, that we have showed that as n goes to infinity, this goes to 0. So fine, as long as my variances are bounded, we have the same means, and pairwise my random variables are independent, they converge in mean squared sense. What about this part, how to prove B? Can we say something about B using A, part A? So when does convergence in mean squared sense implies convergence in probability? Always implies, right? But now I am assuming, I am trying to state this B for the case when my sequence is IID, right? So if my sequence is IID, I know that this already holds. This already holds because all of them have the same distribution, so their means are also necessarily same. What is not guaranteed is though whether the variance is going to be uniformly, they are all going to be same, right? But we do not know where they are going to be finite. They could be infinity as well, right, variance. So if in this case, for this case B, if I make an extra assumption that in my IIDs they are IID, but further I assume that their variance are finite, then we are done, right? Then part A already automatically implies. So part B, if variance finite for all I, then Sn by n converges to m in probability. We just argued that in this case, yes, if my sequence is IID, in addition if I assume that my variances are finite, all the things in part A are already proven. All these conditions in all the assumptions in part A already holds, right? Then under this assumption we have shown that it converges in mean squared sense, and we already know that if it converges in mean squared sense, that automatically implies convergence in probability. Okay, then comes the case, what about if these variances are not necessarily bounded? They could be infinity. So that needs a bit more analysis, so we will skip it. Actually that can be done, we will do a proof later which will have a similar flavor that you can use to prove this part also. Okay, then comes the last part. We want to now prove a stronger theorem that this sequence Sn by n converges in mean squared sense. Okay. So again in this case, I mean it's to prove it in general, in a very generality it's going to be a bit difficult. We are going to argue it like the way we did it for part B under a restricted case. To prove this, now we are going to assume that my fourth moments are finite. So I am only writing the fourth moment of x1 is finite. That means the fourth moment of all the random variables is going to be finite, right? Because I am assuming an IID sequence. Okay. So we already I think sometime discussed, if we know that the fourth moment is finite, then all the moments lower than this are also finite. Fine. So if we can show this under that assumption, that already implies part B, right? Because the part B only required variance to be finite, which is a second order statistics, but whereas I am assuming a bound on the fourth order moment, right? So if I assume this, the second order moment already finite, so that is what I have used to show convergence in probability. Okay, now let us see how, if I assume this, why is that convergence in almost sure sense is true. Okay, again, so this is where the proof of monotone convergence comes into picture. How it comes? First thing to note is Sn, which is the sum of all the first n random variables. If I am going to take the fourth moment, and if I apply further my IID assumption on that, it simplifies to so okay, and also I am going to assume that expectation of x1 is fine 0. I am going to to simplify the argument, we are going to make these two assumptions. One is this fourth moment is finite, second is the mean is going to be 0. If I say x1 is 0, that means mean of all random variables is 0, right? Because this is an IID sequence. So we are proving it under this IID assumption. When x1 of x1 is not equals to 0, this expression becomes too long. So to just to get rid of, see, we have this x4 term, x2 term, then comes the joint terms x1, x2, all pairs and all. So we have to write too many terms. If expectation of x1 is 0, that simplifies and we get this. Okay, now I am going to define y to be a sum of Sn by n but raised to the power 4. So what is this? So this is how to interpret this. This you have to interpret as limit as m goes to infinity summation n1 to n you understand what is the limit of this series, right? It is not a sequence, here it is a series here, okay, and that is like as m goes to infinity and we are summing m and we are getting. Now why this y is well defined, why this I can define like this is a limit, right? I can write a limit when this exists. Now notice that Sn by n I am raising to the even power, so all these terms are going to be non-negative, okay. So because of that, if you are going to look this, so let's take this as ym. So let's say this is now a sequence ym is defined like this. Is this sequence ym is monotonically increasing? Yes, right, because it is adding more and more positive or non-negative terms, and that is true for any omega. You take a omega for that point, and if you do this, so for each omega I have a monotonically increasing sequence, so it will converge maybe to infinity, but it will converge. So that is what that limit I am going to, that limiting value I am going to take it as y. It's fine. Now I have by defining my y as the limit of this ym's, and the way we have defined it is true that ym of omega is going to be greater than ym plus 1 omega, right? This is a monotonically increasing sequence. If that is the case, can I invoke my monotone convergence theorem and can apply expectation on both sides and interchange the limits? So what I want to do is, expectation of y is nothing but expectation of this quantity but now this is a limit, because I have argued that this is a monotonically increasing sequence, I have the liberty to interchange my limit and expectation. Okay. So what we just said is expectation of y is nothing but fine. I mean I'm doing nothing, I'm just playing with the definitions that I have used, and that's fine if you guys have lost already what are the definitions we are using. So but just see that what are the things that we are manipulating here. Now I am going to use my Sn relation from this. So if I am going to do that, the expression I get is okay. Now here what I am going to invoke, the condition that this fourth moment is going to be finite. So I have invoked this condition that expectation of x1 is 0 when I wrote this expression here. So had this expectation of x1 is not equal to 0, there would have been many more terms. Thanks to this assumption I could only write it simply like this, and now I am going to assume, so what I have assumed is this expectation of the fourth moment is sorry, this fourth moment is finite. That also meant that this second moment is finite. This guy is finite here, this guy is finite here, and this guy here is at most n square, and this guy is n, but on the denominator I have n to the power 4. Okay. You can verify that this series is going to so just let us say, I also do not know what is the limit, but let us write it. So this is going to be expectation of x14 divided by n cube plus, so this is going to be what, 3 1 by n square minus 1 by n cube, right, in the expectation of x1 square 2. And I do not think this is not a sequence, right, like this is the sum. So this is going to be a series we have. So this sum is going to converge to some finite value. We can check that, because I know that 1 by n square, summation 1 by n square converges, right. So summation 1 by n cube should definitely converge then, okay. And similarly this 1 by n square converges and this 1 by n cube also converges, their difference is also going to be some finite. So whole of this quantity here, this series is going to be finite, okay. I do not know what is that quantity, but what we are trying to argue is that this expectation is going to be finite. So if this expectation is finite, we know that probability that y is finite is going to be happen with probability 1. Yes, what are the conditions we have established expectation of y is finite. If expectation of y is finite, it must be the case that y takes finite value with probability 1. So this is always true. If expectation of y is finite, then this is true, but the other way is not always true, okay. Fine. So let us quickly complete this. Now the last point we need to argue is how the way we have defined y, we have defined it like this, right, series. If summation of an converges, so if an converges, let us say an converges to some quantity a, what will an look like? Yeah, what where the an's will converge to? It is going to converge to 0, right. So by this we know that my Sn by n to the power 4 is going to converge to 0. Then I can take the fourth root of that and can also argue that Sn by n converges to 0 for all omega. Yeah, I have not yet said that, right, like, so if y is going to be finite with probability 1, right, then Sn by n, that sequence is going to converge to 0. So now we have to argue that this convergence implies the almost sure convergence. Why is that? Because y being finite happened with probability 1, right, and that is what we are using. This implies this. If this is already probability 1, what can be the probability of this? It should be 1, right. Then in what sense it converges? It converges in almost sure sense, okay. So is that clear? Like if this is y is less than infinity, it must be the case that this sequence should converge, this event should happen, and this event should happen with probability 1. So this is the standard result, right, in analysis. Why not? So just you take the contrapositive case. Suppose an does not converges to anything, it diverges. Okay, that means an's are going to infinity. Then do you expect this to converge at all, the series? No way, right? Yeah, yeah, it can converge to infinity, but let's say we are talking about, we have a case where this is finite, right? Yeah, right. So it could converge to infinity, but we have specifically shown that this is a finite case. That's not necessarily always the case, right? For example, take this case, an is to be 1 by n. Summation 1 by n goes to infinity, whereas 1 by n goes to 0. Okay, so let's stop here.